All right, let's take a look at some of these. So a lot of people had this right, this idea of iodine. Iodine, if we compare iodine versus chlorine, iodine is much bigger than chlorine. Why is it much bigger than chlorine? So for example, let me ask you this. This is a trick question. The 1s orbital on, which one has a bigger 1s orbital? Chlorine or iodine? Which one has a bigger 1s orbital? They aren't the same, actually. Oddly enough, they aren't the same. Would it be chlorine? Would have a bigger 1s orbital? Or iodine?
No.
Or smaller. Which one has, let's say which one has a smaller, whichever way you want to think about it. Which smaller, bigger, doesn't matter. Tell me the difference between the 1s orbital on iodine and the 1s orbital on chlorine.
Proton.
Yeah, protons. It has to do with protons. So iodine's smaller. Iodine has a way smaller orbital. The 1s orbital on iodine is a lot smaller than the 1s orbital on chlorine. Right? And yet, iodine is a much bigger atom. Why? The same goes with the 2s orbital. The 2s orbital on iodine is smaller than the 2s orbital on chlorine. Why? Because Z. Iodine has a lot more protons, 53 protons versus 17 protons. The 1s are pretty much unshielded, just very minimal shielding from same shell electrons. Did you guys read about Slater's rule? I didn't test you on it. Slater's rules is a way of guesstimating the amount of shielding depending on where the electrons are. That was the last homework problem in that chapter. So I don't know how many people got to it. But, iodine's bigger because N is bigger. N is bigger means it has a lot more shells. It has a lot more electrons it has to accommodate. And it's going to be based on the Z effective. And so we look at, normally when we talk about size, we just look at the outermost electron. What I said to do in this class is just go ahead and hybridize everything, right? And so when we compare HI and HCl, we're going to compare them, even though in HI we don't need as much hybridization. Why do we hybridize? What was the reason for hybridizing? To minimize repulsions. Well, iodine's a huge atom, and to fit an octet of electrons around iodine is not that difficult. And so the repulsions aren't as great. And so iodine has minimal hybridization, whereas chlorine is a lot smaller and it's going to have more significant hybridization. Now, hybridization varies. We look at the bond angle. Is a bond angle or whatever, although there's only one, there's no such thing as a bond angle here, because a bond angle you need 3 atoms to define a bond angle. Right? And so we don't have any bond angles here to deal with. This is a linear molecule. But, to make the comparisons easier and to make thinking about these easier is we'll just ignore that and we'll treat both of these as being hybridized. Again, Petrucci doesn't do this. Well, Petrucci would be more correct for iodine, but less correct for chlorine or fluorine. Fluorine is going to need more significant hybridization to minimize repulsions. Yeah?
I'm a little mixed up. Like right now when we're looking at this, it's linear, right?
Yes.
But when we're doing the hybridization, we consider it tetrahedral.
Yes.
Because of the electron group.
Right, and therefore we have 2 geometries we always deal with. We have the geometry of the atoms, which is linear, but that, that doesn't tell us what, normally when we think about linear, we think SP, like you did. You were thinking SP, which makes sense, but no, we gotta look, because we can get linear structures in SP, and sp3d and sp3d2 hybridization. We can generate linear structures there. So just because we have a linear structure doesn't mean it's SP. here, we're going to treat both of these as the same, sp3, right? And so what we're looking at is we're looking at the outermost orbital. For iodine, we're looking at the 5s combining with the 5p to come up with the 5 sp3s, orbitals like this. And so when you generate it, well, you know, these outermost orbitals are going to be shielded, like I was telling Scott, it's going to be shielded by the n equals 1, n equals 2, n equals 3, n equals 4 shell. Inner shells are very effective shielders. And therefore, if you shield out all those electrons, then we're just looking at a very big orbital. And so something like this, you know, when we draw it, we draw the large, you know, orbitals like this, relative to something like chlorine. You know, when we're looking at chlorine, it's just n equals 3. So let me draw that over here. And so we're doing 3s, and then hybridizing it with the 3p's, we'll generate the 3 sp3s. We'll have 4 of these orbitals. And when we compare, well, we have less shielding, right? And then these orbitals are going to be a lot smaller. Like this. Okay, let's fill these orbitals up now. When we fill these orbitals, you know, iodine and chlorine, we see both of these are going to have 3 lone pairs and 1 bond. 3 lone pairs and 1 bond. When we have the hydrogens coming in to bond here with the S. Another hydrogen. So we'll put it here. We have our 3 lone pairs. And then we'll put the bond in the plane here. So a hydrogen. A hydrogen 1s is a small orbital. 1s orbital is small. Hydrogen is a small atom. So we'll draw it something like this. We'll have our sp3s sigma bond here. Now, we have 2 electrons in the bond, and what holds the 2 atoms together in a bond? In a sigma bond, what holds the 2 atoms together? The electron density between the nuclei. The electron density between the nuclei can be either in the sigma or the pi. Sigma indicates what? Yeah, and the pi, sigma indicates the direct between the nuclei. Pi indicates that, yeah, they're above or below the axis. And so here, the electron density is concentrated here. We have 2 electrons worth of density that's concentrated. This is what holds the bond together. The more negative charge density, the better, because the nuclei are positive. So, again, these are just probability boundaries. The electron can be found outside, but with lower probability. It's the same thing here. You see the repulsions. Are the repulsions going to be as significant on a large atom? No. You get a large atom, you get a lot more space, so the angles aren't so critical here. You know? So even if they get a little closer together, there's still lots of room. The repulsions here are going to be more significant because less space. Let's see this bond over here. So we got 1 electron. This is an sp3 orbital. It's a much bigger sp3 orbital. Then we have our hydrogen here. Another S. And so again, we make another sp3s bond, but these 2 sp3s bonds are not equivalent. These 2 sp3s bonds are quite a bit different because of the electron density. And when you look at this here, number 1, you know, we'll draw in the same number of dots over here because we have 2 electrons worth of density. But the dots are going to be much more spread out, much more diffused. Number 2, okay, number 1, the electron density isn't as concentrated, so there isn't going to be as big of a pull in towards each other. Okay, number 2, the distance is greater here. And so the bond strength is going to be much weaker. And so here, this is going to have a much weaker bond than that. Okay. On the other hand, I told you that I expected HCl to be a stronger acid. You know, I always think of HCl as being a stronger acid than HI. The reason why I think of HCl as being a stronger acid than HI is it has to do with polarity. Yeah. When I think about this, okay, chlorine has a pretty high electronegativity. If you look at the electronegativity of chlorine on the Pauling scale, chlorine has electronegativity of 3.0. And so what that does is it distorts the electron cloud. I drew the electron cloud quite symmetric, but the electron cloud isn't so symmetric. Because if there's a tug of war between chlorine, which is a 3.0, and hydrogen, which is a 2.1, who's going to win? Chlorine. And so really, this electron cloud is distorted. The electron cloud is what we call polarized. Polarized, you know, when something's polarized, it sets up a pole, like a North Pole, South Pole. But in our case, the North Pole, South Pole is called a dipole because there are 2 poles, the North Pole and the South Pole. That's called a magnetic dipole. What we deal with are electric dipoles, which have a positive pole and a negative pole. We also have monopoles. You know what a monopole is? A monopole just has one pole. Can you give me an example of a monopole? An example of a monopole would be something like chloride ion. Okay, this is just this is the Lewis structure of chloride ion. Which is all its sp3 orbitals are filled. But you know, this is spherically symmetric, tetrahedral, and so this just looks like a negatively charged ball, right? A negatively charged ball. This whole thing has a negative charge. So this would be a monopole because it's highly polar. It's just there's no positive end on this. Really, it's just negatively charged ball. Does that make sense? An ion. And so we work with like monopole things, ions, and dipoles. And dipoles happen like this. This electron density is going to be skewed towards chlorine. If electron density is skewed towards chlorine, what happens is it makes chlorine more negative. Although if chlorine could capture all the electron cloud, it would be like chloride. You see, chloride is not sharing any of the electron cloud with anybody else. Chloride has all of the electron density in this kind of arrangement like this. Actually, we're out of time. Whereas here, hydrogen, you know, it's just a 3.0 versus a 2.1 battle. And so chlorine is going to skew or polarize electron density towards itself and generate a delta minus and delta plus. Iodine's electronegativity I don't have memorized, but it's a lot smaller. So in iodine, this is going to be a lot less polarized. And so the delta, you know, minus and the delta plus here are much less significant. And so if you're a base, which one would you be attracted to more, HCl or HI, if you're a base? If you're a base, you're definitely going to be attracted to HCl more. You know, base like hydroxide, what does hydroxide want? It wants an H+, right? And so for sure, HCl will be attacked more because it's much more attractive. And HI is a lot less attractive, but so the H pluses come over here, your base, the H plus is here, your base, you try to pull off the H plus, it's harder to pull off here. You aren't as attracted to this, but this H plus is a lot easier to pull off. Do you see?
So if you're a base, it's going to be important.
That one for sure. If you're a base, you're going to attack this one. But the problem is you're going to have trouble pulling the hydrogen off. Depends on how strong of a base you are.
But HI is still the stronger.
HI is a stronger acid, not because it's the more attractive one, but because it's easier pickings. Does that make sense?